Greetings, Woodians and School of Lifers. We're going to do something a little bit different this week. We're switching over largely from doing business analysis based discussions to doing general text subjects with hopefully a wider range of participants. Also, there's only so much to say about business analysis, so off we go. I actually did this presentation in Baltimore about 6 years ago now, which is kind of scary. So the certifications are out of date, and these slides are still hosted in Reveal.js, but they're in their native habitat on slides.com. So I will go into some of that next week. In the meantime, we'll talk about the subject at hand. I was inspired to do this because I was attending the Baltimore JavaScript meetup, and I saw a guy do a talk on the Three.JS framework. He gave an introduction that was pretty effective. His slides are still up on his website, so I will invite you to go check those out. And this is 6 years later, and mine are still here too. And the reason this was interesting to me was I took a computer graphics course in college that was 1984, where I learned the here's the textbook for the course, Principles of Interactive Computer Graphics. And that's where I learned how to do the representations and matrix transforms for all this. And I've followed developments in the field to a degree. I'm not an expert graphics guru. Everything I do is fairly utilitarian, not photorealistic, but it's good for engineering work, gets the job done. And not a lot of people can do it. So if we're going to do 3D graphics, we have to have an agreed upon way to set this thing up. So if you think about a 3D coordinate system, we'll do a right-hand version. So you have X and Y the way you would look at it, right? Hopefully this is showing up correctly. It's backwards as I'm looking at the back of my hand, but you should see it front ways. And then if we add the Z coming forward, as we would with our right hand, that's how we define the three axes. Now, if you notice left-hand system, if we put them backwards, the X and the Y could be defined the same way, but the Z's go in the opposite direction. And this makes a difference when you define rotations and so on. So we have an agreed upon way to do this. The rotation around the x-axis is actually in the direction your fingers curl. So it's harder to think about how things happen on the around the other axes, but that gets you at least part of the way there. So I talked about that. Yeah. Okay. So here is the way we set up a web page to get the basics going. And I don't necessarily expect you to follow all of the details in code. Know that they're here. There are plenty of sources online that talk about how to do stuff. I'll give a general overview of how it all works. So we have a basic HTML page with a head and a body. And we define a canvas that is the same size as the entire page, right? And so what we're going to be doing is drawing all the stuff on the canvas. It's a graphic canvas, it's a bitmap. We're turning individual pixels on and off to generate lines in shaded areas. So that's what's happening. And in reality, we have a two-dimensional surface onto which a three-dimensional scene is projected. So we need the math to do all of that. So we talked about an aspect ratio we have to define. We have to define a camera, which is where we're looking from and to. And hopefully where we're looking from and to will be visible within the view of the camera. So we have to set that all up. And then we have a renderer. So we're going to render the part of the scene. And we have a canvas, which is pointed or a member of the DOM. And then we start appending things to the canvas and define the scene. And then anything, that's just the basic boilerplate to set up the 3D work. And anything we're actually going to render goes in here. Now, what you ought to be able to do is I will have a number of examples of programs in this presentation. They are all rendered in iframes, so they're individual HTML files with the requisite HTML boilerplate and JavaScript code independently. So you should be able to pull those down one at a time. If you have any trouble doing that, let me know and I'll make the actual codes available to you so you can see these things one by one. So let's talk about how to draw a single line in 3D. So we're going to define these endpoints as X, Y, and Z, 1 and 2, and we'll define a line color, right? And then we have to define a material, and the material is actually what describes how the rendered image is going to reflect light. And then we basically create some geometry and we push these things onto a stack. Or that's the way. It's been a while since I've seen this. We add this to an array. And then we go ahead and add it to a scene. Now we build a grid, so we'll do some increments from 3 to -3 in the X and Z direction in increments of 1/2. So the dimensions of a grid, we can make it 1,000,000 for every grid, or we can make it 1, or we can make it 1/2, and you'll see how this works. So we basically march from -3 to 3 in increments of 1/2, and we draw a line. If we're drawing the line at 0, we'll make it red, otherwise we'll make it blue. And hopefully you will realize that these are colors specified in hex as R, G, and B. 2 letters each, or 2 places each, from 0 to 255. And so the 0 will be, not 0 will be blue, and 0 will be red. We do that for X and Z. And the way this looks, so we define a direction or a point to look at, which is the origin of the picture. We'll place the camera somewhere out of the scene, and then we'll render the whole thing. And it looks like that. So if you notice, we've gone -3, 2.5, 2, 1.5, 1.5, 0, it's red, then 1/2, 1, 1.5, 2, 2.5, 3. And we do the same thing in the Z. So there we go. It's on the XZ plane. So if you think about it, what you're looking at, you've got your X and Y traditional flat thing you could draw, but we're now drawing on the XZ plane, so you can see it sitting here. And graphic systems are usually defined almost always as right-hand. It's a convention. It's consistent. If everyone does the same thing, then that will eliminate or lessen confusion. So we started with just doing a few lines and made up a surface. More complicated objects like a cube, for example, or a sphere, are made up of more lines. So a cube would be 6 squares basically, and they would share points in lines where they run into each other. And the way computer graphics works, the modern way it works, or the way they figured out quite a while ago, is a lot of things are easier to do if you work with triangles. The math and the processing is simpler. So you tend to define meshes with all triangles. And you also have to define where the origin of each object is. So if I define a cube with a height, width, and depth of 1 in the picture or the scale we just witnessed, then it might sit at the origin, and it might go from -1/2 to +1/2 in every dimension. Maybe we'll make it a little bigger. So the way Three.JS works is it defines objects based on their center. So if we have a cube, and this is a really bad way to show it, if you imagine something with a size of 1 along each edge, and the center would be halfway through it in each dimension. Because of the way the math works, if you did a rotation transform, it would rotate around the center. So if we actually define a cube to start at one of the corners on the outside and you did a rotation, it would not rotate around its center, it would rotate around that point in some way. And the way early systems actually defined objects was it would have all their points the way they were or wherever they were in space, and then they would have to translate them to the origin, do the rotation, and translate them back. And what Three.JS does is it defines a center or an origin for all the separate objects, so we can do the transforms on them in place. I know that's hard to follow as a bunch of verbiage, but trust me, once you get up to speed on this, it makes a lot of sense. And there are many different operations you can do. Rotate is the obvious one I've discussed, easiest to see. But there is also scale, so you can make an object bigger or smaller. And there's shear or skew, which means imagine turning a square, pushing it over on in one direction, askew, and turning it into a rhombus, right? So you're kind of flattening it out, pushing it over, turning perpendicular lines into diagonals. All right. So shapes are made up of a geometry which shows where the edges and surfaces in the center are, and material which shows how it interacts with light and how you're going to see the thing. And materials are usually applied to the individual surfaces, and if we make them small enough, they'll all run together smoothly over curved surfaces. So if you can imagine a cube with a bunch of physical surfaces, and you have light shining in from some direction, and a ground, you can imagine all the faces having different brightnesses as they reflect light from different angles. In the they may scatter light in different ways, and they may cast shadows. So there are a lot of things that can happen. We cannot make a sphere infinitely smooth as a graphic representation, but we can define one out of a reasonable number of triangles so that when the shader does its thing, it'll look comparatively smooth. And there's a whole pile of math that goes into how these shaders work, how the surfaces work, and so on. The presentation that Chris Eulinger did actually one of the examples mapped the picture of a side of a crate to every phase of a cube. So it kind of looked like a wooden crate with a frame and a diagonal piece on the outside and all the slats in a shadow, but it just pasted them flat on every surface. And if you rotate it, you kind of lose the 3D effect unless you actually model all those individual elements in 3D, but you can see all the different things you could do with surfaces. So let's add an element. We'll make a box of that is dimension 1, right? 1 on the slide. We'll define a basic material. It'll be green in theory. And we'll add a geometry and material to the mesh and add it to the scene. And this is based on this XZ grid that I showed you a minute ago. So that is thrilling right there at the center. You notice these grids are in elements or increments of 1/2. So if this box is 1 on a side, it runs from -1/2 to 1/2 in every dimension. It's about the most thrilling thing you can imagine. Now, let's make it do something. The way animation is done in JavaScript, it actually just renders in a loop. When you set this thing up using request animation frame, and it does that up to 60 times a second if the render process doesn't take too long. So if the render process takes longer than a 60th of a second, the frame rate will slow down. And one thing, when I was teaching myself JavaScript graphics like 6-7 years ago, I found out that the way the system works is it clears the canvas and redraws everything from scratch every single time. So one of the things when I was first learning graphics on the Hercules graphics card on a PC with 2 floppies in 1983, the graphics would be persistent, and in order to move a shape around the screen, you'd have to erase just that part or XOR it on and then move it and re-render it. But you would leave a lot of the scene alone as much as possible. And this was because the computers of the time were so slow. But now you just do everything from scratch. So here we're going to animate this. We're going to rotate the cube in a positive direction around the x-axis, so it'll look like it's rotating toward you over the top. So let's see if that works out. It's kind of an optical illusion, but that's what's happening. So it's not too much more exciting, but hopefully it's a little more exciting. So I talked about having to translate things to the origin, to the rotation and back, because of the way Three.JS defines things kind of independently. It really shortens a lot of that work. So ideally, one of the things you also had to know was how, if you have a list of points, the matrix multiplications you could do, which I could talk about in detail to make a plane rotate or shear or translate or scale, right? Um, there are ways to do all those things. You don't have to know how it all works. It just does it for you. There are good descriptions out there of how the matrix math works. I've done this by hand in the past. So here is a thing I wrote in the mid-90s, just playing around with 3D graphics. I wrote it in Delphi a long time ago, and it was it's an animation of an induction melting furnace, which basically has metal coils running around the outside of a ceramic vessel into which you pour scrap metal or some kind of raw metal. You run a high current through it, and it eventually creates an alternating magnetic field in the center of the coil where the metal is, and it eventually melts this. And you scrape the junk off the top and then pour it into molds or whatever. So I charge and melt. So if you can imagine pouring loose metal in, it'll take whatever shape the junk will take. You can define a packing factor, and when you melt it, a liquid fills the volume in the shape that it's in. So if I keep hitting this charge button, the kind of cyan ring shows where the top level of the loose metal is, and I'll charge it to the top, and then I'll melt in, and the liquid level will keep rising, and I'll keep doing that till I get it over 75%. So we've got that now, and now we can tilt this thing down, and then the weight will actually go down as the liquid starts to pour out of the thing. So we can rotate this thing around various axes, and I did a really crude hidden surface removal. It was by hand. It was really Cro-Magnet. It was based on the rectangles. I think you saw a screw up there where it actually drew a couple of lines it shouldn't have drawn. There we go. That should not happen. So the point is that if you know how all these things are done, you can do them. It's doing all the matrix multiplications, do all these transformations, and a few other things as well. So that was definitely this JavaScript framework works way more easily. So let's add a couple more items. We'll add 2 more cubes like the first one. So the first one will make it a mixture of red and green, which should, I think, come out as yellow. And the second one will be green and blue, which should come out as cyan, right? And one will put 2 on the X and -2 on the Z, so it'll be back and to the left, back and to the right of the original cube on the level of the grid, and the other one will be floating above the grid in the other direction in front and above and to the left of the cube. So that's what's going on. We have our center one, yellow one back right, and cyan one front left and above the plane. So that's what's going on there. And they're all rotating around different axes. This one is rotating positively around the x-axis, which is the horizontal red line. The yellow one is rotating positively about the y-axis, or its own vertical line, which is straight up and down, and a line coming kind of into and out of the page. It's the z-axis, that's the line around which the cyan object is rotating. So what I'm doing now is showing you the same scene and showing you how I'm gonna rotate the scene by changing or rotating not the picture, but the way we look at it. So what I've done is I've animated a make-believe camera that shows where I'm going to be looking from. We always look at the origin, and then we define an X, Y, and Z location. And if you define a location and where you're looking at, it does all the angles for you. Of course, for this picture, I have to figure out how to draw the actual camera cylinder at the right angle. So here is how we create the camera. We define face and vertex colors. We define a cylinder, and that's part of the framework. We're talking about certain parameters, diameter, the number of faces, and so on. There's a way to do the actual surfaces, and we stick that together and stick it in the scene. So down here, and yeah. One thing also we have to do is, so if we define a cylinder, right, it finds the origin at the end. So I wanted to transform it, or it to find the, it to find the origin as in the center, but I had to shift it out to the actual end. And the surfaces in the wireframe have to be in sync and translated the same way. And we'll define a light, which we're doing directly above the scene. And there are some parameters for the light here, and here's the position, and here we're adding it. So the yeah. So then what I'll do is draw the actual lines that show where the camera was. So that's what all those are. Yeah, and then we actually draw them. And we'll initialize a few things. So here's some rotational bits. And then we will rotate the viewing point around the scene. So that's how we actually created the previous scene that I showed you. And then we, as part of the render, we go ahead and rotate all the cubes. We do the rotation of the camera, and then we do the animation render. So we're moving the camera here. I cannot move it left and right. It's doing the automatic rotation around the scene, but what I did, oh, not yet. I'll get to that. So this is looking at the scene instead of I could rotate the scene and leave the camera steady, or I can leave the scene steady and rotate the camera. So that's what's happening in this render. So that's actually a lot simpler. You see the math, I don't have to go through all the crazy things I did in the previous one. Now let's have a little fun. I will actually define some actions to move the camera up and down. It's always going to be looking at the middle of the grid, and I will have it be able to move in toward the center and back out. And I'll define the key codes that allow that to happen. So this is how you handle key events in JavaScript. It's just gonna do some basic keys. Right and left don't do anything, but it shows you that you could handle things that way if you put some code in here to do it. I could do the angular rotations of the viewpoint, for example, rather than having that happen automatically. But the up arrow will move the viewpoint up, which actually talks about moving the camera height up to some maximum that I've defined. The down arrow key will move the viewpoint down. The B key will move it backwards or away from the origin, and the F key will move it forward, and the home key will restore the initial settings. So let's look at this. Here's the initial scene, just like we had. We'll hit the up arrow key, so now we're looking up from a higher height. It'll get more fun if we look from below the scene down to some level. We can make it actually look from directly edge on, so the plane almost disappears. Let's move back up to make it kind of like it was, move forward into the center. and move back away. So now we have a video game-like thing where we have motion through the image. And there are a lot of ways to do it. Again, what we're doing here is we aren't moving the actual scene, we're moving the viewpoint. So there's two ways to do everything. Now, there are other ways we could send events to this little graphics program. We could use a game controller. This was the status of what things were supported in what versions as of early 2017. If you follow that link, there are way more versions that support things. I could program all these things to take controller inputs of various kinds. There are way more devices and way more OSs on different devices. I looked at this the other day. There are CAN uses for an immense number of different APIs and bits of hardware that different browsers support. So I didn't actually do this, but you know that happens. So if we change the we can change a few things about the camera. So we have a point of view, right, that we're looking from, but we can make the field of view wider or narrower. And that changes the perspective and things like that. And this allows you to see what to do when the screen size changes. So what I'll do is I will open an independent link. Can you still see that? All right. Let's take it away from full screen. And I'll change the size of the screen. And if you notice, the scene actually changes size with the size of the window. And so what we're doing is keeping the scene kind of proportional to the window. And get rid of that. Go back to the original. And if we think about this, right, here's some math to calculate how we're changing the window. If we make the scene change with the window size, it'll change size, but if we want to be able to change the window and leave the scene the same size, we have to do some math, and this talks about the geometry of how to do that. Here's how it implements all that. And here is all right. So there's two things going on here. One is just for kicks. I applied the stereo JS filter to it that takes the scene and doubles it. So if you look at it in a 3D viewer like an Oculus or something that'll mount a phone in a thing that mounts on your face, it's actually showing these things from two slightly different views. And if you looked at it through the correct kind of viewer, you would actually see it in 3 dimensions. So let's go to the independent link. And ideally, what should happen now as we change the size of the window, and this only applies to the vertical dimension, the picture will not change size. So there are a lot, the point of this is there are a lot of things you can control in these, and you have to be aware of what you're actually doing. Hopefully this is clear as I'm talking about it. I know it can be a little difficult to follow. So here's a system I wrote. I probably showed you this in the first lecture I did about 3-4 months ago now. It's a discrete event simulation framework. All these different objects are defined separately, and they're all stitched together. It's a totally modular system. And here's how it looks in 2D. And here's it automatically generates graphics in 3D in the same configuration. And when it's done, it does a bunch of statistical calculations for every time period and so on. And I can reset it and run it again. And I could pause it, and I could step in, either by time steps or individual steps, or I could just run it. So I talk about the process of developing the whole framework and how to do a discrete event simulation, some other math, all the graphics and so on. Here's a blog. There's 92 blog posts about this. And here's the direct page that links to all the same stuff on my website. If we just want to look at the 3D animation on the similar kind of grid I showed you before on a slightly different scale, here it is. It'll basically just run over and over. And the colors for these things show when the object is busy and is waiting or will make other entities wait. Here's a parking lot which disgorges other entities like people you can imagine, and they go through some other process. They come back to their car, then they drive away. So there's a lot going on there. Now, one of the interesting things in that scene was, if we're doing a simulation like that, we might not know how many entities we're going to create, those little cones that were running around the scene. So this bit of code talks about creating a whole bunch at the beginning and storing them off camera someplace way far away where they can be seen, so they can be called and place in the scene and have their color change as they're needed, as they're visible, and then they can be shunted back off scene again. So that's what is going on here. We're going to define each entity. So it's a cylindrical cone. We talk about the bottom radius, height, number of segments, surface, and some information about the shading and offsets. I think I defined there may be one high or two high, and I shift them up so the center is actually at the bottom. And when I do transforms, it puts them in the scene at the correct place. We draw the wireframes and we put them in the scene, or give them new locations, or we send them out of scene. So I defined, here's where I've set the position and the color, or I put them way out of the scene. So the X and Y coordinates are 10,000. So even if you would look in a direction where you see them, they'd be so small they wouldn't show up. And then here's how I update them. I have the model has a list of where these things are. So every time I update and render the scene 60 times a second, it'll grab an existing one, define it, put it where it needs to be, render it, and start the whole process all over again for the next render. And this is better, I think, it's faster than making a new one from whole cloth every iteration that we do. All right, the final thing I've got for you is that rendering text in 3D is actually proved to be fairly complicated. These are actually, I labeled the x-axis and the z-axis here. And they actually rotate on a plane in a way that you can always read them, that rotates with the scene. And they're on a transparent background, a rectangle, but I had a fiendishly difficult time figuring out how to put these things where I wanted, modify them, and so on. And I just did not get the hang of it. There are a lot of discussions around the web for how to make this happen. Doing stuff in 2 dimensions for text is difficult enough if you're just projecting onto a flat screen. If you know about the history of Apple computer, Steve Jobs' big thing when he created the Mac was to have it do really good-looking typography and fonts. And now imagine trying to fill in all the serifs and details of every part of a letter to make it look really nice, but now project it at a completely arbitrary angle and point of view in 3 dimensions. So that gets very complicated. I put the code in for how to do that. I won't go into the struggles I had within. Someday I should figure out how to do this better. A lot of times what people will do is create some kind of a raster bitmap and project it onto a surface and then have it rotate in that and render that, and that kind of does a lot of the work for you. It's not as direct or as pretty, but it also works. But like everything, it's all about trade-offs. So that's what I've got to say. If you dig into this code and dig into the information about Three.JS and WebGL, you'll find a lot of the basic information and it'll get you sorted. Like I said, all the different renders I showed you are standalone programs that exist on my website. You might be able to download them directly by doing an inspect and finding out what the link is, and just copying into your own computer and running them in a browser directly. Let me know if you need help with that. And that's all I've got for today. Thanks for hanging out with me.
Good, thank you. I don't have any questions, but that was a good walkthrough of the framework.
Yeah, it's a way to get started, right? All right. Have a groovy win.
Did you see my Tau shirt?
I did. I couldn't tell what letter it was. What does it say?
It's 2 pi. Tau is 2 pi.
Okay.
It's kind of it's like a joke, agenda that we're pushing this adoption of the new symbol. And the fine print here is just the numerical value of 2 pi.
I like it.
Mm-hmm. Yeah, very fortuitous that I wore the shirt today.
Sounds great. I always love nerdery in all its forms. So have a great week. We will see you next week.